Bismillahirrahmanirrahim. Assalamualaikum and hello everybody. So my name is Rani Muslim bin Ahmad Tajuddin, and today I will be presenting a summary of a journal which is entitled Simulation of Fick's Verification of the Second Law. So to start off, we'll be starting off with the problem statement, which is Fick's second law was never described in complete detail. So the objective of this journal is to verify Fick's second law, as his experiments were never described in complete detail or the scheme explicitly sketched out. The authors only assumed that they resembled the vessels shown in Figure 1, in which on the left here we can see Fick's cylindrical vessel. The white cylinder above the cylindrical diffusion vessel represents the fresh water reservoir. And on the right here we can see that Fick's funnel-shaped vessel. The white cylinder above the conical diffusion vessel and represents the freshwater reservoir. Okay, to continue, the research methodology here is a case study. So, as a simple introduction, adopt Fick's now famous salt diffusion experiment, in which Fick layered sodium chloride crystals at the bottom of two differently shaped vessels connected to sizable freshwater reservoirs served as initial confirmation of his second law, but was never described in full detail. The connected reservoirs at one end of the diffusion vessels were continuously refilled and clean water throughout the experiment as salt molecules diffused up and out of the vessel and were eventually replaced by water molecules. So densitometric studies of the natrium chloride or sodium chloride concentration profile by Fick demonstrated that a right circular cylindrical funnel produces a linear fluctuation of density with distance down the funnel at a steady state. So you can see Figure 1 on the left, instead of a linear concave upward plot of density against distance, the conical funnel, like the one in Figure 1 on the right, produce a non-linear, which is a concave downward plot. So these experimental findings supported Fick's now famous second law of diffusion by agreeing with his theoretical calculations. Additionally, Fick established the crucial idea of interdiffusion coefficient by quantitative comparison of these experiments with theory. So here are the solutions to Fick's second law. The first one starting with a theoretical approach. So it is simple to develop analytical solutions for the concentration field and steady-state diffusion in 2 or 3 dimensions. So we can see here in equation 1, C is the concentration of the salt at location x and time t. D is the interdiffusion coefficient for salt and water at the temperature and pressure used in the experiment. And A is the locally variable cross-sectional area through which interdiffusion occurs. The change in concentration with time vanishes as time approaches infinity, and in equation 1 becomes the linear ordinary differential equation. So now we can see here in 2 dimensions the area is different, and in 3 dimensions the area is also different. So as a result, the differential equation for diffusion in the 2-dimensional vessel has the coefficient of 1, while the differential equation for the diffusion in the 3-dimensional case contains the coefficient of 2, such as below. So the next solution is by boundary conditions. Now, it is possible to provide the boundary conditions for the steady-state diffusion fields, which are the same in both scenarios. When equilibrated at a fixed temperature and pressure, the layer of salt crystals at the base of the vessels will eventually fix the concentration of the solution at its equilibrium solubility, or Cmax. Thus, the system is subject to the following constant concentration boundary condition: the layer of salt crystals in R square and in R cube ensures that, such as below. The second constant concentration boundary condition on the diffusion field is established by the presence of a sizable pure water reservoir connected to the vessels at x equals to 0, which is continually refilled to remove any salt traces that diffuse out of the vessels. The pure water reservoir in R square and R cube ensures that, such as below. The last solution will be by steady state solutions to Fick's law in R square and R cube. The steady state concentration field solution for R square can be expressed as equation 9, while the equivalent solution for R cube is as equation 10. After a few steps of algebraic manipulation and the substitution of the non-dimensional identities, such as here, the funnel vessel's shape can be changed by decreasing omega max while increasing omega naught in one of three ways, in which the first one, to one with equal values producing either a rectangular diffusion channel in R square or a right circular cylindrical diffusion channel in R cube. And the second one would be to one with equal values producing a broad opening at a pure water interface and a narrow base where the salt layer is placed. And the last one would be to one with these shapes. Figure 3 shows a steady state concentration charts for 7 distinct funnel shapes derived from these analytical solutions, as we can see here in figure 3. Next, we finally get to see the random walk-in simulations in R square, my bad. For reasons of data correctness, efficiency, and CPU time, the random walk simulation for the diffusion exchange of salt and water molecules was only performed in 2 dimensions. Next would be the simulation rules. The number of random walks to be averaged, the number of steps in each walk, and the step length and precise values for omega max and omega naught were chosen to start the simulation. Lambda, actually the standard deviation of the Gaussian random process, which was fixed at lambda equals to 0.1. Along with this choice, the number of steps n was fixed at 10,000. This choice ensures that the particles were able to make multiple trips over the full length of the diffusion path, which was fixed at 10. These choices assure satisfaction of the greedy state requirement. For the case of a rectangular channel, which is defined as having a height of 10 units and a width of 2 omega naught equals to 2 omega max equals to 1 unit, there are 1000 water molecules present at the beginning of the simulation. Over the course of the simulation, the total number of molecules does not change, but the identity does, as will be explained below in figure 4. For the cases where omega max equals to 2 omega naught or omega naught equals to 2 omega max, the resulting rectangle used in the initial placement of the water molecules has a width of 2 units and a height of 10 units. The result of this rule was that 2000 points were placed in the rectangle. So figure 4 shows the initial placement of the water molecules when omega naught is twice as large as omega max. Once the simulation started, every walker moved once per cycle without taking into account the positions of the other walkers when When a walker of either salt or water encountered the horizontal boundary located at omega max, the walker was deemed to be salt molecule. Thus, the performed walkers do not accumulate at either horizontal boundary. The side boundaries also act as reflecting barriers for both water and salt molecules. Both types of walkers underwent elastic collisions with each side walls and were reflected back into the diffusion channel without changing from one molecular type to the other. So it wasn't essential to regulate the stride of duration to get rid of the so-called edge effects, because the simulation specifically considered what occurs when one sort of walker runs into the opposite border. However, when figuring out how many steps were necessary for the random walk to produce correct findings that fitted with the necessary steady-state diffusion criteria, the step length became crucial. The number of steps in the random walk needed to obtain adequate walker displacements decreased as step length increased. So next here are the simulation results. So figures 5, 6, and 7 shows the results of several simulated cases for different diffusion channel contours, as seen here. In the final walk of 100 trials required to calculate the average concentration, these data plots displayed the parameter beta, establishing the channel shape and the steady state positions of all molecules. In these plots, the blue points represent the water molecules and red points represent salt molecules. So in figure 8, a single point represents the quantity of particles in a bin that is 0.2 wide as a single point. The jagged lines from figure 8 are created by connecting these plots with straight line segments, and the error bar associated with the average of 10,000 random walks are shown here in figure 9. So, only until the particles had repeatedly diffused from one end of the tapered channel to the other could the simulation's steady-state condition be said to have been reached. And the steady-state condition was therefore not yet reached. The steady-state condition is reached after roughly n equals to 10,000 steps with a step length of lambda equals to 0.1. Only then do the steady-state diffusion results from the random walk-in simulations show sufficient agreement with the analytical continuum results. So, as a conclusion, by recreating his well-known funnel experiments from 1855, in which the diffusive flow area can change, Fick's second rule was tested numerically. Following the derivation of Fick's second law in 2 and 3 dimensions, and a random walk simulation in 2 dimensions was used to verify 2-dimensional continuum theoretical results. These findings demonstrate that long random walks can in fact be utilized to reproduce with controlled errors the outcomes of Adolf Fick's original salt experiments when given a sufficient number of trials. Comparing these steady-state continuum diffusion solutions to random walk statistics, they perform extremely well. These simulations must reach steady-state conditions in order to produce accurate findings. In order to achieve this, the molecules must at least traverse the entire diffusion channel. The number of steps required to reach steady-state diffusion conditions decreases as step length increases. Similar to any random walk simulation, the better the agreement with continuum theory is produced, the more trials are included in reporting the average. So that's it from me. Thank you.